Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's my pleasure to introduce Alex Aiken. Alex has been my PhD advisor at Berkeley, and but that's not what he's famous for. He's well known in the area of yeah, that's right. He's well known in the area of set constraints, both on the theoretical side and practical side. He's worked on this decidability results and complexities, semantics for types in the form of set constraints. But on the practical side, he's been working on many program analysis based on set constraints. And although he tells me now that you can do anything in set constraints as long as it points to analysis. Well, he's going to talk more about related analysis today, which is effective static race detection. And I forgot to say, now he's at Stanford, actually, no longer at Berkeley. So, please.
Okay. Thanks, Manuel. And I want to thank John Spencer, who's absent, for inviting me up here to give a talk today. So, actually, I'm going to talk about the word set constraints will not appear in the talk at all. It has nothing to do with set constraints. In fact, I'm going to give my first ever program analysis talk. I'm not going to give a single type rule, a single implication rule, nothing. Okay, so it's going to be a novelty for me. And I'm also going to talk about a topic on which many people in the audience actually are more expert than I, which is the analysis of concurrency. But just in case it's very unlikely in this audience that there won't be anybody who already doesn't know what a data race is. But just to make the talk self-contained, let's recall that a data race occurs when two threads access a memory location, and at least one access is a write, and there's no ordering imposed by the execution of the program on which of those two accesses happens first. Okay, so the accesses are unordered. And there are lots of situations, well, I shouldn't say a lot, there are situations in which races are considered to be benign, but that's pretty uncommon. And so as a rule, races are considered to be bad. Unfortunately, they're very common, or believed to be very common in large concurrent software systems, and they're known to be very difficult to find. And the main reason for that is that because it's a property of execution and non-deterministic scheduling, it's very difficult to reproduce races. So it may be here today and cause a problem for you, and then when you report the bug and try to go and find it again, it doesn't want to reveal itself. All right? And the classical example that you'll see in every database textbook on races is something like this, where you have two threads. They're incrementing some shared variable, and depending on the order in which these increments happen, you may wind up with the value being incremented by 2, or incremented by 1, or if these are floating point numbers, and you have a double word representation, as you do in Java, and you have no locks on these things, you might wind up with complete garbage, because one thread will wind up winning the race to write the high order word, and the other word will win the race writing the low order word, and you'll just get some nonsensical thing that was not ever computed by any thread as a result. Okay. Now, here's my stab at previous work. Okay, there's a lot of previous work on analyzing concurrency. And I actually started out with this talk, I was going to give a more complete taxonomy of previous work. But when I went into the various online citation indices and just started looking through the papers and trying to decide what to list and what not to list, I decided the risk of insulting somebody was far too great. And I would just say, well, there's a lot of work. Okay? And it's been going on for a very long time. I'm going to drill down a little bit here at the beginning of the talk and just say, there are two broad classes of work, the dynamic work and the static work. And on the dynamic side, it's pretty clear what the state of the art is. And in fact, just in race detection in general, in practice, what people actually use out there in the world are variations of the eraser algorithm. Okay, to the extent that people use race detection at all, they use eraser. And the idea behind eraser, it's worth going over that because it will come up again later in the talk, at least when I discuss how we differ from other kinds of work. The basic idea is that every shared location it must be protected by some particular lockx. Okay, what that means is that every time you access that memory location, you will hold the lockx. All right? Now, there's a couple of assumptions built into that idea. One is, first of all, that you have lock-based synchronization. Okay, there are other ways of doing synchronization, but Racer is really about locks, and most race checking work is about locks, and our race checking work will also be about locks. So for the purposes of this talk, let's just pretend that locks are the only way to do concurrency control, and we can discuss alternatives at the end of the talk. All right? Or if you want to ask questions along the way, feel free to interrupt me, I should say. The second thing is that you can only have a particular lock that's going to guard that location. So it's not okay, for example, to use the lock A for a while to guard the location and then change your mind and use the lock B later on. Even if you're being perfectly consistent and everybody switches, and uses the new lock at the right time altogether, that's not a paradigm that a racer would recognize as correct. Okay? You're allowed to have one lock for each memory location, and that lock is fixed for the entire program. Right? Now, if your program satisfies that assumption, then there's a nice dynamic technique for getting at whether you have correct synchronization, and that's just as you run the program, every time you access a shared memory location, record all the locks that were held at that point in time. Okay? And you just remember that for every single memory location, and over time, you just see if there's one lock that's being held consistently. And you can do that by intersecting the sets at every access. You just keep one set around for each memory location. Every time you access that memory location again, you intersect the set of locks that are currently held with the set you remember for that location. And if that set ever becomes empty, then you know you violated this desired invariant, and you will report there's some difficulty with that memory location, some possible races on that memory location. So, as I said before, this is a dynamic technique, and this inherently has some disadvantages. So believe it or not, despite my history in static analysis, I've actually done some work in dynamic analysis, and in all my work in dynamic analysis, I learned one very important thing. It's really a pain to have to run the program. Okay? Because before you can even do your analysis, you have to construct some data. Okay? And this is a world of hurt for anybody who is interested in program analysis. Getting these data sets together, running the thing, keeping it all organized, having even more than one data set so you can actually get variation in the executions, it's a lot of work. Okay? And it also excludes lots of interesting situations in which you might like to do checking. Like if you don't have a whole program yet, you're writing some library and you'd like to check that thing. Okay? If you only have a piece of a program, it could be very, very large. A racer doesn't really help you, okay, because you don't have something you can actually run. You don't have an executable. In addition, you get false negatives that arise from inadequate coverage. That's the classic problem with any dynamic technique. And false positives are also possible. That was a particular paradigm, okay, and as I illustrated before, there could be false positives for some obscure reasons. There are also more common reasons for false positives with a racer. Okay. It's also very difficult to implement it well. Naive implementations have orders of magnitude slowdown, and there's been a huge amount of work actually on efficient approaches. And I think this right here is probably most indicative of how much people want tools for race detection, because a racer is generally regarded as the most, probably the most pragmatic idea that has been proposed, and just the amount of effort that has gone into making it run fast enough that you can actually run long-running computations with it has been rather phenomenal. Okay, and despite these criticisms, it is the state of the art. I think I think most people would not argue that this is what people use. But arguably, this is not a very natural idea. I mean, when programmers sit down to write their code, I don't think they think in terms of what set of locks they're holding at a particular point in time, and whether they're not thinking in this dynamic execution framework of I'm holding this set here and this set here, and the intersection is not empty. They have some different model, a much simpler model, I think, in their minds for why their code should be correct. Now, static approaches, there's a lot of these too. People in this room have worked on some of these, and as I said before, I think I'm a relative newcomer to this area. Roughly speaking, they would be classed as type-based model checking and data flow systems. Okay, and I will say a few words about them as we go along, but one thing is they all have in common is they find relatively few bugs. Okay, so if you actually look in the papers, read the results in the experiments figure on page 9, the number of bugs that are found is relatively few. So typically less than 10, often less than 5. Okay, the system that found the most is RacerX, done by Dawson Engler. I think it's the one that has the biggest bug count, and that found 16. Okay, in 1.5 million lines of operating system code. All right. So what's going on? Well, there's a couple of reasons for this. Well, one is that if you are into relatively coarse techniques, meaning something probably more tending toward the data flow side or or a very simple type-based system, something that will scale reasonably well because the algorithms are inherently not too expensive, but they're too coarse to really do a good job, and you're either overwhelmed by false positives or you just throw out so much stuff that there's not much left to find. Okay, and so the techniques that scale to very large systems typically have not found very many bugs because of the precision. And then the techniques that are precise, if you look in the papers, they're generally not applied to large programs. So tens of thousands of lines is typically the biggest applications that you see. Okay, I don't really mean this as well, it is a criticism. It explains what we're going to do differently. Okay, and I'll motivate that in a minute. But also a lot of the work in concurrency has not really been geared towards, the purpose of the work was not to build a tool necessarily for people to use. Okay, a lot of it was to explore foundations of concurrency and try to get the concepts right. All right, so a lot of this work would fall into that category where this criticism here is kind of off base because that wasn't really what they set out to do in the first place. All right, but our goals is to do what we call effective, and effective is supposed to be a code word for finding the many races we believe are out there in the big programs with a static technique. Okay, so do something that's going to work as well as a racer, be as usable as a racer, only be more usable because it'll be static and you won't actually have to run the program. Okay, yeah.
Is there evidence that dynamic techniques find a lot of bugs?
Yeah.
So,
Yeah, if you work hard enough at it, you could eventually find them all. So,
a version of a racer frequently.
well, that's a good question. Now, I would have trouble answering that with a lot of confidence, but I believe that so for example, IBM, there's a huge investment in. They're one of the groups, the research groups at IBM, put a huge amount of work into making a racer efficient. Of course, IBM has a huge investment in Java. Okay, and then the work they did was for Java. So I believe that it actually, that was motivated by the needs of, at least in part, of development groups inside of IBM.
And then there's the Cook and Associates that got bought by Intel. It has a threading laboratory that has variations on this.
Right. Okay. And our methodology here, unlike a lot of my previous work, okay, is very bottom up. All right. So basically, we want to do what works, and we will come back and try to explain why later. All right. Now, it's not going to be quite that bad. So we'll have some. I will give you some reasonable explanations as we go along, but it's definitely an experimental piece of work. All right. And our goal was to have something that we could actually run on large programs, and to use it on real projects. So we picked open source projects that were very active and large, and ran it on those, and showed the results to developers and got their feedback, and used that to decide what to do next with the tool. So this is basically the milieu in which we operated. Okay, and after doing this for a while, we came across some criteria we think that any effective static technique is going to need, some properties it's going to have. And some of these are obvious, maybe all of them are obvious, but they've never, in retrospect, they've never been all together in one tool before or in one piece of work that I'm aware of. And these would be precision and scalability. I've already talked about those. The ability to handle a variety of synchronization idioms. So even within locking-based synchronization, there's several different styles of locking-based synchronization. It's important to be able to deal with those. I talked about open programs, meaning programs that are incomplete, that are not complete executable. And finally, the ability to produce counterexamples. So probably with race detection, more than any other kind of bug reporting problem that I'm aware of, you really need to produce a trace that shows the bug. Okay, because just saying there is a race on field X is not useful, because nobody knows what that means unless you show them actually the execution that will cause that race. And this is one of the more novel things maybe that we did, the way we present the counterexamples, or it comes out of the particular approach we took. And so when I get to that, I'll dwell upon it a little bit in the talk. All right. So here's the basic idea. So this is going to be a deflationary technique, meaning we're going to start with a big universe of possible races, and we're going to gradually cut it down to a small set. So we'll basically start out with all read-write and write-write pairs, and then successively refine that set of pairs using a series of program analyses, each of which evicts some pairs from the set. Okay? And then the final result will be what we consider to be a good set of potential races. Now, as I hope I inoculated you in the previous slide, we didn't set out to be either sound or complete. So we set out neither to find all the races nor to avoid reporting any non-races. And I will say more about this at the end of the talk. Okay, so we do actually understand in what ways it is not sound and not complete, and that's the work we're doing now, is to try to extend the tool, towards being a completely sound tool. But the version that I'm going to report to you today, leaves a few gaps, and I'll explain how we bridge those for the moment. All right. So I said the basic idea was to run a series of program analyses that would cut down the set. And so here is my little picture of what we do. So we start out with all the syntactic pairs. Okay, and then we successively run 4 separate analyses in this order, producing first what we call the reachable pairs, then the aliasing pairs, the escaping pairs, and finally the unlocked pairs. Okay, and this is really an outline as well for the talk. So I'm going to now walk you through each of these steps and what they do. And as I go along, I'll make comments on, hopefully provocative comments that will get you to ask me questions and generate some discussion. But before I do that, I need to say a couple words about open programs. Okay, so as I already think I'm motivated, analyzing open programs, at least I believe, is a really important thing to do. Okay. Because a lot of programs that people develop are libraries, and the unit of development is often a library. So there are entire development teams out there that don't ever write a complete program. They just write a library which they give to other people to use. And these developers need tools to help them understand the behavior without the existence of a client, and especially without having to write lots of different clients to exercise that code in all possible ways. All right. So now I'll say that even among static approaches to program analysis, and this has nothing to do really with concurrency, it just goes to the culture of the different communities doing static analysis, not everyone considers open programs to be so important. So if you look at the bug finding work that's typically done, or the type community, they really start from the premise that they're working with an open program. There's no assumption that you have a complete program. But a lot of model checking work, for example, at least historically, does assume that you have a complete program to begin with. Okay, so it's a little more foreign concept maybe, if you're looking at this from a model checking point of view, to consider using open programs. That's not to say there's no work in model checking and open programs, because I know there is, but it's not the dominant paradigm in that community. Okay. So the standard approach, if you have an open program and you want to do some relatively sophisticated analysis on it, say a model checking based approach, is to write what's called a harness. Okay, and the harness is a fancy name for the client. You basically write the rest of the program, okay, and then link it to your to the thing you actually want to analyze, and then you analyze that closed program. So you have a complete program and you go off and analyze that. All right, and our approach is to generate that harness automatically. Okay, so we're going to have an automatic harness generation step. If we have a closed program, we're going to complete it with some code that will then exercise it in appropriate ways. And here's how we generate a harness. Okay. Now, so the first thing, so let's consider a method M, which is part of the interface that we want to check. Okay, so we assume that we know what the interface is, the set of public methods that are exposed. Okay. So we will create a variable v of each type of an argument or result of M. Okay, and that will go into the harness. And then for each v, we will assign some concrete object of a compatible type. Okay, and we'll use new x as needed to create such objects. And the reason that we may assign more than one is there may be subtypes that we need to worry about. And so in different places in the harness, we'll try out different combinations of possible types of objects. And then we'll construct a call to M for every legal combination of arguments chosen from these variables. Okay, and each call will be in a different thread. Okay, and the v's will be thread shared. So all these variables we're making up here are thread shared. We're basically going to construct every possible call and put it in its own thread so that all these threads run concurrently, and then we will check that closed program. Now, there's a few comments to make about this. So how do we know that this is a good approach? All right, so what does it mean to generate a good harness? Okay. Well, that's actually an interesting question, which it turns out has not been well investigated. All right, there are some approaches, if you look back in the old day, in the ancient history of type theory, little bit in model checking where people have kind of stumbled across this a few times. There are some ideas out there, but nobody's ever looked at this systematically. And you know what? We didn't either. This went on our future to-do list because we had this other goal we wanted to get done first. But this is definitely something we plan to come back and look at again now that we recognized it. The issue here is that whether it's a good harness or not is intimately connected to how powerful the analysis is behind it. More powerful analyses behind it will be able to distinguish more clients. So if you have a very simple analysis, you don't need a very complicated client to exercise that analysis in all possible ways. The number of distinctions it can make is relatively few. Okay, yes?
As you're going in this direction, I may have lost the point of
This is a digression.
how this is static as opposed to dynamic.
Well, we're writing code here to turn this. So you give me a piece of a program that you want to analyze.
Right.
But I'm going to generate a client, meaning a main program, a main method. And I'm going to stick onto that will exercise that. Okay, but it's all static. I'm just generating code. And then I'm going to analyze that completed program.
You're not going to actually.
I'm not going to actually run it. No, I don't have to get any data. Okay. Yes.
What about the situation where races may happen because you invoke a method M1 and then a method M2?
Yes. So let me get to that. Okay. So just hold that thought for just a moment. The question was, what about races that could happen because first you invoke method M1 and then you invoke method M2? Okay. So without going into too many details here, we don't know whether this is sufficient. In fact, we know this is not complete in the sense that it doesn't exercise the client in all possible ways, even for the analysis we have. Okay, but it is close because our analysis is what's called flow insensitive. So it doesn't need to know about order. Okay, so it's sufficient to have all the things be independent. It doesn't care about the order of statements particularly. All right, so that in that case, so at that particular point, we don't have to worry about. There are some other features that are missing to make this absolutely complete. But from a practical point of view, it does a pretty good job in terms of the number of races it finds. Yeah.
So for client-side locking, actually the client that you generate would actually have to take a lock for this particular paradigm. Otherwise, you will see races.
Yes.
I'm sorry?
So if there's no thread safety inside of the library you're calling, and you're doing it at the client level, this would see this as, of course, a race condition.
Right. So the assumption here, at least, is that the thread safety is done inside of the client. I mean, sorry, inside of the library. The library, is supposed to have a thread-safe interface. Okay, you're presenting a thread-safe interface to the world, and we're going to check that. That's true. So yeah, if there's supposed to be some locking discipline that's observed by the application, our harness generation is definitely not sophisticated enough to exercise that. Yeah.
Also, you only do half of it. You only do calls.
Ah, very good, very good, very good, very good. What about calls out, right? So we do calls in, and what about like missing native methods and stuff like that? Well, we don't have any great new ideas there, so I didn't put it in the talk. We do what everybody else does, which is write stubs or ignore them. Yeah.
But there's another calling out, calling back to the client.
Yeah. So callbacks. Yes. Yeah. So callbacks. We're not currently dealing with callbacks either. That's correct.
But that shouldn't affect the internal state of the call.
Sure it can.
Yeah. No, okay.
Why not?
Well, it doesn't.
Yeah.
It doesn't.
Sure it does.
Yeah, let's see, I guess. Yeah, it's still an interface. Yeah.
Okay. All right. So here's a little running example which we'll use for the rest of the talk. And don't try too hard to understand it because it's an artificial example constructed especially to illustrate how wonderful this technique is. Okay. So there's 3 public methods. There's a constructor. There's one integer field in this class. Okay, and that's f. Okay, and there's a get and an inc method. So this is something that reads that field f. This is something that does an increment, but in a very peculiar way, which will illustrate some technical points later on. Okay, and then there's 2 private methods, one of which does a read and one of which does an update to the field. Okay, and that's all there is. Now, for the first step, we have to make this is an open program, so we have to make it into a closed program. We'll generate a harness that looks something like this. Okay, there's only one type, so we'll have one variable of that type. We'll assign it a new object of that type, and then we'll call the public methods in some non-deterministic order. Okay?
The first star is a type, right?
The star there refers to a non-deterministic choice.
But the first one you don't want there, right?
Well, for a flow-insensitive system, it doesn't matter.
Okay.
And this is actually there for technical reasons. I mean, you're right. From a pedagogical point of view, this is a mistake to have in the talk because it attracts questions like yours. From an implementation point of view, there's actually a reason it's there because of the peculiarities of the infrastructure on which we're building. Okay. All right. Now, notice one thing about our harness, though. I said that each of these calls needs to be put in a separate thread. And in fact, this harness is single-threaded. And this is a detail. Our system knows which method is the harness, and it simulates it being multi-threaded. It doesn't. We don't go through the pain of constructing different threads there explicitly ourselves. We track that inside the tool. Okay. All right. So back to the story. Okay. So open programs, we deal with that by closing them. The idea of what it means to be a well-closed program for the purposes of some tool, it depends on what the analysis is, and it's actually an interesting problem, but not one that we're dealing with in this talk. Okay. So what's step one? Step one is what we call original pairs. We want all the pairs of accesses such that one of them is a write, and they refer to the same field. Okay, so they refer to the same field of the same type. And for this talk, I'm just going to deal with fields. We'll ignore arrays. We'll ignore static fields. Okay. Our system does handle both. This is again just pedagogy. That it's this is the most interesting case or the most the crux of the matter, and we can discuss this if anybody's interested in to hear what we do. Okay, so coming back to this piece of code, where are the field reads and writes in here? Well, there's two writes, one in this private method, one in the constructor, and then there's one read in that private method. Okay, and those are the only field reads and writes in this little piece of code. Okay, so now for illustration, what I'm going to do is I'm going to make two copies of the code. Since we're talking about pairs, the idea is we're kind of running this thing in parallel with itself. So over here will be our read or write, and over here will be the corresponding write. So at least one has to be a write, and then the other one can be a read or a write. Okay, and so what are the possible pairs that could arise? Well, this first stage is just purely syntactic. We're just looking at all the reads and write accesses of fields in the program, and we just pair them up in all possible ways. And so there are five possible pairs in this case. Did I leave one out? That doesn't seem quite right.
No, one was you're making the right-hand one always be a right. So.
Right. That's the reason. Okay. Anyway, so there are five possible reads and writes, pairs of reads and writes, or writes and writes. And now we're going to make a first approximation that we need to do. We're going to ignore, for the moment, and actually for the rest of the talk, but I'll come back to this at the end. We're going to ignore all the pairs that involve constructors. Okay. Now, why do we do that? So we're only going to look at the pairs that arise inside of methods outside of the constructors. Okay. Now let me say a little bit about why we do that. Well, this has to do with our choice, which I haven't yet motivated, for using what's called a flow insensitive analysis. And for those of you who don't know what that is, I will get around to telling you at some point. But for the moment, let's just assume let that label hang. Okay. And it turns out that you get a lot of false positives in constructors if you use a purely flow insensitive race checker. And the reason for that is twofold. First of all, objects, when they're being constructed, are not shared. They haven't been built yet, so they haven't been communicated to any other thread. So they're private to a thread during the time the constructor is running. For that reason, programmers know this, okay? And so they don't protect those objects with locks, okay? And for that reason, also, races in constructors are relatively rare, okay? Now, not impossible, because a constructor may be manipulating other objects at the same time that are thread shared, but the object itself that's being constructed, is not going to have a race on it. And without flow sensitivity, the unprotected accesses in the constructors look like races. Okay, now let me define flow insensitivity for you. So a flow insensitive analysis is one that produces the same results regardless of program statement order. So within, you can permute the statements of a program in any order you like, and you'll get the same result. All right. Clearly, the fact that a constructor is unshared while the object is being built, and then later it becomes shared, that's a flow-sensitive property. You have to know the constructor comes first, okay, and during that period there's no sharing, and then later on it might get communicated to somebody else. So there's clearly an ordering there. Making use of that fact requires knowledge of the order of execution. So that's why flow-insensitive analysis, falls down there. Yes.
So I saw escape analysis on your slide.
Yes, you did.
It seems like that escape analysis would eliminate the actually
the actual non-races in constructors?
Yeah, let's come back to that. Okay, but mostly because I don't have an answer to your question right away. I need time to think about it during the talk when we get. But the appropriate place to discuss that is there. All right? If I think of a clever response, I'll give it at that time. Otherwise, I'll just pretend I forgot the question, and we'll go on to the end of the talk. Okay. So our system is flow insensitive, and so it's like type-based systems in that respect. And unlike essentially well, I don't know of any flow insensitive model checking system. It would seem to be a oxymoron. So we ignore constructors, and the best justification for this is that a lot of other people do this too, for the same reason. Okay. Now, some more comments on flow insensitivity, because this is going to turn out to be one of the major design decisions, and actually later on we'll talk about how we undo it, and so this is or what we're doing to undo it, which is why this is not so much of an issue. Dealing with the constructors. So in general, though, flow insensitivity is going to hurt precision because it's going to weaken your interprocedural reasoning. You're not going to know the order of statements inside of a procedure. All right, but it helps a lot with scalability. Okay, to a first approximation, flow insensitive analyses scale much better than flow sensitive ones because you don't have to maintain separate state for every point in the program. Okay, you don't really care about which point in the program you're talking about. Now, how much precision is lost here depends on the synchronization idioms that are used in practice. Whether this decision makes sense at all to use flow insensitivity really depends on how synchronization is done. And one of the reasons we went with it was because the dominant way of doing synchronization in a language like Java is to use a lexically scoped construct. In the case of Java, it's a synchronized keyword. Right? And so you see a lot of stuff like this where there's a synchronized on a method, and so you know that the lock is held for the duration of that method. It's acquired on entry to the method, released on exit from the method, and so you know exactly the scope without having to do any kind of flow-sensitive analysis. Okay, so you get that information for free, and so then you can make the rest of the analysis cheaper by making it flow insensitive. All right. Now there is another synchronization paradigm that comes up a lot, though. You see a lot in real programs, which is fork join. Okay, and fork join requires flow-sensitive analysis in order to understand the scope of where the lock is held, because the programmer places the fork in the join explicitly, and you have to reason that, from this fork I traverse these statements until I get to the join. So in order to know where the lock is held, you have to do something with program order. Okay, so this is where flow sensitivity is really useful. Now we decided, again, this was another decision to help us move on with the bigger goal of building something effective. Rather than go back and add flow sensitivity at this stage, we decided to use annotations. Okay, because we observed that, in fact, the kinds of false positives and the kind of loss of information we got from the lack of flow sensitivity here was actually quite minor. All right, there were examples, but there weren't a lot. And in addition, the fact that you needed in order to get rid of the false positive was, in many cases, a very simple fact. And in the end, we came up with two kinds of annotations. We only required a total of 42 and 1.5 million lines of code. So that's like an annotation per between 30 and 40,000 lines of code. And what these annotations say is, these two groups of methods cannot be called in parallel. Like this interface and that interface are never called in parallel on thread shared data. So just ignore all of those. Okay, that's one kind of annotation. The other kind of annotation is at the method level. These two methods cannot be called in parallel, concurrently on thread shared data. So ignore any races you observe between those. All right, and so the ability to declare this at the interface level, where you can take an entire group of methods and relate it to another group of methods, turned out to be a very useful thing to do. Yeah.
But you don't do anything else to check it. You just trust the program in that case, right?
We just trust the programmer to do this in this case, right? Now, since then, since this work was complete, we're now working on removing those annotations and putting in the flow-sensitive analysis that we need, to get rid of that. But in every case, we actually checked these by hand afterwards, and we've never found a false positive as a result of this. So I'm confident. And the lesson there is that the amount of flow-sensitive information that's actually needed in these applications to analyze fork join synchronization is actually very small. Okay, you do need some. You can't do it with zero, but the amount of flow-sensitive the number of flow-sensitive facts, or the difficulty of acquiring the flow-sensitive facts that you need is minimal.
Is that because there just aren't that many uses of join?
No, it's not so much. Well, that's one thing. People don't use the join a lot. Yeah, people fork and they don't join. Okay, that's one thing that happens. The other thing is that programmers themselves only use fork join in very structured ways. I mean, they're a little, for the most part, they're not trying to do anything too clever with it, and so it's pretty easy to. I mean, the information really is there interprocedurally. It's not that you don't. Inside of one procedure, you can get the information you need. You don't generally have to go off and look at the things it calls and the things that calls to get the flow-sensitive stuff that you need. Okay. Yeah.
What about barrier synchronization? That is.
Yes, we don't deal with SPMD. We don't deal with SPMD style synchronization here. Yeah, that's another style. We can talk about that. That's actually worked on that problem years ago in another context. Yeah, it's not as common. It's not as common. So I don't have anything really intelligent to say about that in the context of finding races.
So futures in future versions of Java, they're proposing futures as a standard language feature. So
yeah, I haven't followed that. Futures, yeah, futures make me slightly nervous, although I find it difficult to say why on my feet. Okay.
Fork join with a vengeance.
Yeah, I mean, it's worse than fork join in the sense that the time at which the join is done is now implicit. And now, the fact that people leave join out so much and it doesn't hurt us, doesn't seem to hurt us, makes me think that maybe it wouldn't be that bad, but I don't know. Yeah, I just don't know. Okay. All right. Okay, so back to the story. Step 2. So let's now, so obviously not all of these, just because you write the same field or the same type, that doesn't mean that you have a race. Okay, so what are other conditions that are needed to have races? So let's consider any access pair that came out of the first step. So to be a race, a very weak condition that's needed is that both of these accesses must be reachable from some thread spawning site. So there must be some place that spawned a thread and some execution path would actually get you to those access sites. Okay, they can't be dead code. All right, that's all right. And in addition, the thread access, the thread spawning site also has to be reachable from main. Okay, now there's one more condition in here. All right, which is that you want it to be reachable from a thread spawning site S without switching threads. Okay. And what does that mean? That means you would start at one thread access site. In order to reach the right, say, you would have to pass through another thread access, another thread spawning site. Well, in that case, that right wouldn't be part of the first thread that you started from. It would be part of the second thread. Okay, so that condition is really there to cut down on the number of pairs. Instead of enumerating it for every possible thread site, you're only going to enumerate for the ones that can actually reach it without going through another place that would spawn a thread. Now, there's one more thing here that's important. Okay. Is that this is where we're going to start to add context sensitivity. Okay? And this, if there's a silver bullet, a secret sauce in this work, this is it. Okay? That the context-sensitive analysis was really crucial to all the results. In fact, beyond this first syntactic phase, it's used in every analysis. Okay? So everything here is going to be very context-sensitive. And the other thing that's interesting is that the standard notions of context sensitivity, the ones that dominate the literature, none of them worked. Okay, so we tried simple stuff like control, I forget what it's called, class hierarchy analysis. That's an old one due to David Bacon. That's very, very simple. That wasn't nearly precise enough. We tried control flow analysis, which if you're a type person is a standard kind of polymorphism that you see in ML, okay, where you're keeping track of who called who called who called who. Those notions just don't do a good job. Okay, and the kind of polymorphism that actually does pay off, and the only kind we use, is object sensitivity. Okay, this turns out to be the notion that just from a purely experimental point of view, trying these things out and seeing which one worked best, this was by far and away the best. Okay, and it's a relatively new notion of polymorphism. It's only been in the literature for a couple of years, so it's conceivable that you might not have heard about it, so I apologize if everybody knows if this is all very familiar to everybody, but I'll just define what it is. So object sensitivity distinguishes objects by the call stack at the point where the object is allocated. So at the point where you say new, you make a record of the call stack back to main, okay, and that's the label for that object. So the same malloc or new site, the same place where you allocate an object, you can actually get distinct abstract locations depending on the calling context where that constructor was called, where the new was created.
Just a thread ID.
Is it just a thread? No, it's not a thread ID. It's
Is it the call stack?
yeah, the usual notion. I mean, usually, if you analyze, usually the number of abstract locations you have in an analysis will be determined by the number of new sites, or in the case of C, malloc sites. So you'll have one abstract location per place where you can allocate memory. Okay, this is for making distinctions in the heap. Right, and now we're just going to say, well, instead of doing that, we're also going to keep track of the call chain at the point where the malloc happens. So you can have as many distinctions now as different ways of calling each of these constructors, each of these places that allocates memory.
The call chain.
The call chain, the call stack at the point where the thing's called. All right, now we don't actually try to keep track of the entire call stack. Okay, we keep track of some suffix of it. And in this case, we use k equals 3. All right, so that will turn out to be sufficient in our experiments. Okay, and one of the things we did, which I'm not going to talk about at all, is that it turns out that none of the public implementations that you can get of object sensitivity actually works for k equals more than 1. And we needed k equals 3, and so we actually had to redo it from scratch. And so we had a new implementation of object sensitivity for this particular piece of work. Okay? Now, so that's how objects are distinguished by their call stack, and then methods are labeled with the context of the this parameter. So whatever labels on the this parameter, that's what the context is for a method. Okay? So methods calls are distinguished by where the object was allocated. Now, for intuition, why is this a good idea? So think about constructing a hash table. How do you construct a hash table? You call some hash table constructor. So it constructs some backbone for the hash table with a bunch of buckets, and then maybe it allocates a bunch of stuff under that, to be headers, say, for each of the buckets. Okay? And so you have a data structure that has 2 levels deep when it's allocated. Okay? Now think about that second level. Well, if you just do it by malloc site, then if you allocate a hash table here and a hash table here in your program, they're going to get conflated. Okay? Because they were allocated by the same program point. All right? If you use k equals 1 object sensitivity, they're also going to be conflated because they were called by the constructor for the spine of the hash table. All right? And then the thing that allocates the headers all got called from the same place. But if you use k equals 2, now you're back to the point in the program that actually said, OK, I need a new hash table. Then it builds this multi-level structure. All right? And you have enough levels of call stack recorded that it has to be as many levels as the structure is deep, okay, in order to give you the distinction that you want. All right, then you keep track of, well, this particular hash table is now distinguished from that particular hash table, and not just the top level of the hash table, but also the things inside. And that's what's really useful. Okay, when you have these big data structures, you don't want them, they're used a lot in different places. It's complicated data structures, you don't want them all smashed together. All right, especially not just at the top level either, also further down inside. And that's where the context, the object sensitivity really pays off. All right, so let's take a look. So now in this carefully constructed example, we don't even really need sophisticated object sensitivity. We just need to distinguish the 2 malloc sites. So we'll have 2 contexts, A and B. Something that's allocated here and something that's allocated there. Okay? Now, where does context A go? Okay, and that really means, where does this object flow? What things get executed in context A? So all I'm going to do now is paint everything red that can run with that object as the this parameter. All right? So all those things clearly, A goes to all of those, and then A goes to all of these things. So the read, the get method, the inc method, these pieces of it use that object. Okay, this piece over here does not. It's still in blue. And then the read method and the write method can both be called with A. Right? If we look at the other context, which arises from the other allocation site, the only things that can be called in this context are this call to WR and then the stuff inside of WR. All right? So that's the only pieces of code that execute in that context. All right? So the read function can be called in context A, and the write function can be called either in context A or context B. Okay? And this is object context now. All right? So now the next step is that we're going to keep so now the reachable pairs are going to be what I said before about threads. So something has to be reachable from some thread starting point. Access has to be from a place where a thread is spawned. The access has to be reachable from there. And we're going to record each such pair of contexts now. Okay, so we're not just going to record the accesses themselves, we're going to pair them with every possible context in which it could happen. So now we're going to distinguish context-location pairs. All right? And so what are the set of reachable pairs? Well, we started out the set of syntactic sites that could be possibly involved in arrays were these. Now we're going to include the possible contexts to make more distinctions, and that looks like this. Okay, so there are 6 possible reachable pairs. There are 6 reachable pairs in this case. Now here the red line indicates that this one is in the red context, and the purple lines red and purple here encode the context. Okay, so for each possible pair, one of the accesses could be either in the red context or in the purple context. Okay, and so you can see here, these are all the possible ones. All right, not my most eloquent statement, but I think you get the idea. All right. Okay, so now what about the next step, aliasing pairs? So this is just a recap of steps 1 and 2, so you can remember what they are. So for step 3, so in order to have a race, both elements of the access pair, they have to access the same location. You can't have a race unless you're actually accessing shared memory. Okay, we haven't even talked about that yet. Okay, so we're finally getting to what you actually might think of as something that has to do with races. And here we're going to use the aliasing information. All right, and this aliasing information again is a flow-insensitive, object-sensitive points-to analysis. Okay, so it's essentially the same thing in which using the same infrastructure that we talked about in the previous step. And these points-to relationships are context cross-location pairs. Okay, the things that you can point to. So two accesses are going to be aliased if their points-to sets are going to share a context-location pair, saying they can point to the same location in the same context. All right. Now, if we come back to our example, okay, because this example is very simple, all right, the contexts here, this is the context in which the access executes. Okay, so this is executing in context A. This one over here, the purple one, is executing in context B. The accesses are equivalent to the location that's being accessed because it's this parameter in each case. Okay, it doesn't have to be that way, but the example was specially constructed so we could show this visually. All right? So what that means is the only things where there's actually a possible race are where these edges are the same color in this example. Okay, because you can't have, if you have an access in context A and another access in context B, they're talking about different objects. They can't possibly involve a race. They're not aliased. Okay? So in fact, oops, forgot to click earlier. Okay? So in fact, there's only 3 accesses that survive this test in this example. Okay, so these are the 3 now still candidate races that we have to worry about. Okay, so there's 2 on object A, and that's the object that's allocated at this site, and there's 1 on in context B, that's the object allocated over at this site.
Actually, A is some other site that's not shown on this slide.
Okay. Oh, that's right. You're right. Sorry. This is, yes, the main procedure I've removed here because we have our duplicate code, right? The one that would be here if we weren't showing a separate copy, you remember that, is the one that's for object A. Okay. All right, now, escape analysis. So now what is this about? Well, in order to have a race, not only do you have to have pieces of code that execute in the same context, that are accessing an object in the same context, that object has to be shared. Okay, so you can't have a race within a single thread. So any object that only stays within a single thread, can never have a race on it. We should eliminate all of those at some point. All right, so to have a race, the memory location must be thread shared, meaning it must be able to be accessed by more than one thread. So how do we do that? Well, there's 2 ways it can happen. The main way that we're interested in for the purposes of this talk is that an object could be thread shared if it's reachable from some argument of a thread spawning call site. Now, what does that mean? That means that I spawned a thread and I passed it a parameter, okay, that reaches my object. All right, so let's forget about the reaching part. Let's say I pass it the parameter. Well, that parameter is not going to be thread shared. It was passed from one thread to another thread that got spawned. And transitively, anything that's reachable from that object at the time it was passed will also now be reachable in both threads. And that's what the reachability condition is there for. Okay? And this could also be true if it's reachable from a static field, since anybody can refer to a static field. Any thread has access to static fields. All right, and the real goal of this is that access on objects that are private to one thread are going to be ruled out. Okay? So this is another one of these analyses. I'm just stating it here in English, but it involves reachability. It's going to involve context, and it's going to be looking at the objects in the thread sites. All right, but now if we apply that here, what can we see? So what we can observe is that this object here it does not escape its thread. It's never passed to another thread. So it's created here. It's used in this call, which doesn't do anything interesting with it, and then it dies. Okay? And so the analysis will be powerful enough to determine that, in fact, this guy here cannot escape.
Al?
Yes?
And your analysis there also then looks at the code of WR to see that that's...
Yes.
Right.
Yeah, I mean, it's the whole, yeah, it does the right thing there. Okay? So that leaves us with two possible races. I'm getting a little concerned about time, so I'm going to go slightly faster. If anybody wants to stop and ask questions, feel free. So finally, the last step is we look at the locks. Okay? We haven't even done that yet. And in step 4, we're going to discard pairs where the memory location is guarded by a common lock in both accesses. All right? And this is actually perhaps the most involved step. And let me motivate some of the decisions that were made here. So what locks can be held at access point A? Okay? And this is a generic A now. All right? And the locks that can be held at any given point where you're having a memory access, whatever they are, they must have been acquired on some call path from main to A. So by starting at the access point A and looking back through all the contexts that we're remembering, back to the main method, we can just look at what locks were acquired along those paths. Okay? Now these are call paths. These are chains of calls. Remember, we're not flow sensitive, but we are context sensitive, and so we know the call chain. All right, and we can look and see if there's any synchronized statements, for example, along those call chains. And we know all the possible calls. We know all the possible ways in which they were called. All right, so version 1 would be, well, so take any call path to the first access point that still has survived, take any call path to the second access point that has survived, and then see if they have a lock in common. Okay? Now that turns out to be extremely expensive, enumerating all the possible call chains. All right, so we actually use an approximation to that, which is we first compute the set of locks that are required in all contexts for each access. So we look at an access and we say, what locks are required in every context? Every way you could call to this point to reach it, what locks are always acquired? And then when we want to compare two different access sites, we intersect those two sets of locks and see if they have something in common. All right? Okay. Now there's a second approximation we make, which is, what does it mean to share a lock? Okay, if I say if access point 1 acquires lock A and access point 2 acquires lock A, does that really mean they acquired the same lock? Because remember, these locks are also abstract values, and they might stand for more than one concrete lock, because we're using may alias information, not must alias information. So really, to be sound, you would need must alias information at this point. You would need to know that they were in fact the same lock. And that would mean that that set was singleton, that there was only one possible value that had been allocated there. And actually, in a lot of cases, because of the simple ways in which people use concurrency, you can do that without a lot of trouble. But we don't do it. We actually use the may alias information as an approximation. Okay? So both of these approximations are unsound, both the way in which we summarize which locks are acquired, okay, and the way in which we don't use must alias analysis, to determine whether it's actually the same identical lock. All right? Okay, but if we apply these approximations, what do we get? So we have, where did it go? So if we look at this, if we look at the right, okay, the right is guarded by this synchronization here, which I've abbreviated with sync. Okay, so the inc method is guarded with a synchronization. That covers, that rules out the possibility of this right executing in parallel with itself. However, if we look at the read, which we'll do in a minute, we'll see that there's actually a race there. But first we can eliminate this candidate, and we're left with one candidate now. Okay? And if we put back in the main program here and look at what this candidate is telling us, what does it say? So look at the get method. So we can call the get method. That would take us over to this code here, and it calls the read method, which is going to read this location without a protecting lock. Okay, so the write method is going to be, the inc method is going to be synchronized, but I could call the inc method in parallel with the get method, and that would generate a race condition. Okay, and that's what our tool would report in this case. All right. Okay, so the implementation of this, well, it's built out of borrowed parts, like a lot of research things. We use Soot, which is a Java framework from Laurie Hendren's group at McGill, and we use BDDB from John Whaley, and the analyses are all implemented in Datalog. So it's a massive collection of rules, and actually each one of those analyses is fairly complicated. My one-slide simplification in English doesn't do justice to the complexity of these analyses and all the cases that need to be covered. So it's actually one of the more complicated analyses I've ever seen in terms of the number of different phases that are pasted together. And it's all solved in the back end using BDDB. Okay. Here are some of the programs, or actually all the programs that we've looked at to date. The smaller ones are included because they've been used by previous static tools, and so they're good reference for comparison and experimental results. The big ones we picked because they were big, because they were public, and because they were active. And so there were a lot of developers working on them, and we could actually post bugs and get feedback on the bugs.
What do you do about the standard Java library?
Some of it we model with stubs, okay, and some of it we ignore. So we just treat it as no ops. I mean, either we put in a model, if it's a very commonly called function that is relevant. I mean, and after doing a few of these, we figure out which ones are the most important, and otherwise we treat it as a no op. And over time, as we invest more effort, we add more of such stubs. Okay, so here's the experimental results, and I'll spend a couple of minutes on this if anybody wants to know what happened. The biggest one is Derby, which is a full relational database system. Running time's not too bad, about a half an hour in this case. And it's about, I think it was over 500,000 lines of code, maybe 650,000 lines of code. And you can see here, actually, how much effect each phase has, it varies a lot. I mean, in this case, the reachability step cuts down a lot, by order of magnitude, almost an order of magnitude. But then not much happens until we get to the analysis of the locks at the end, when it drops dramatically. Okay? And the interesting thing here about this particular example is that all the races were harmful. These were all due to bugs. Okay? There was not a single false positive in there, not a single benign race. Now, why are there 319 bugs and 1,000 races? Because some of the races can happen in more than one context. Because remember, we're tracking all the possible ways the race can arise, and you might have the same access pair being called from a few different places that will result in multiple races for that same pair of accesses. And our tool will give you many counterexamples as you like, but it'll tell you how many races there were. And then we have to go through by hand to classify them into bugs. So the bug classification piece was done by hand by looking at the races and saying, oh, these are really the same field that's being raced on and things like that. Okay? So we got very few false positives in general. And the cluster in these smaller programs, and these were all due to lack of flow sensitivity. Okay, so we'd added flow sensitivity, we would be able to remove those. There were benign races, and there's really not a lot we can do about that, because benign races are races, and our tool is supposed to report them. So a benign race is something where you actually didn't care if there was a race. Something like you're updating a counter in a profiling tool, and you don't bother to protect it with a lock because you don't care if your count's exactly right. I mean, you'll lose some updates, but so what? Okay, but our tool will still report those. Yeah.
So how concurrent are these applications? How many threads?
Well, these are highly highly concurrent. I mean, these are transactions. Some of these are transactional systems. Derby, JDBF, JDBM. These are designed to have arbitrary numbers of threads running against the and these are mostly open programs too. The bigger ones are mostly open. Okay. All right. So let me go on. I have a few more comments on the results as we go along. So here's our criteria scorecard from the beginning. So in terms of precision, I think it's fair to say the false positive rate is low. The false negative rate, of course, we don't know. But for the smaller programs where people had run other tools, sound tools on them, we were able to check whether we found all the bugs that they did. And we found every bug that all the sound tools found. Okay, so on the same examples where the sound tools had been run, same version, we found our tool reported the same bugs.
If you have a closed program, then the only source of unsoundness in your analysis is the lock analysis. Is that right?
If you have a, no, I don't think so.
Context.
No, there's a little bit due to lack of flow sensitivity too. I mean, but I don't think that's as serious. The locking piece is the most serious source of unsoundness. Let me move on here because I'm not sure what people's expectations are about the end of the talk at the time we finish. So scalability. So there's good news and bad news there. I think it's fair to say we handle bigger programs than any other static tool by an order of magnitude, I believe. Okay, other than the very coarse ones that I mentioned at the beginning that do something very simple over very large programs. However, there are still some larger programs that we can't handle yet. There are some bigger programs where we have to do more engineering to get the tool through. But the fundamental context and sensitivity underneath it leads one to believe that it'll be that's a solvable problem. Synchronization idioms, I already mentioned that we handle the synchronized keyword, and we also handle fork join with some annotations, and we're working on removing those annotations right now. So we're working on adding enough flow sensitivity to remove that issue completely. Adding the must alias analysis, which I think, to be more specific to answer your question, the real source, the most serious source of unsoundness, or the most difficult to remove, is the need for must alias analysis. Okay, flow sensitivity piece is not that big a deal. All right.
Flow sensitivity, lack of flow sensitivity only lead to false positives, not negative, right?
Well, except that because of the lack of flow sensitivity, we cut some other corners too. So, that's really I'd have to think about the answer to your question. So I don't want to say anything wrong. If your goal is to be sound, then not having flow sensitivity is only going to add more false positives. Okay, but we didn't set out to be sound, and so there were some places where we made some decisions, that we knew would throw out some races. Okay, because of the way things were set up, and flow sensitivity played into that. The way we treated fork join synchronization is not sound. Okay, all right, and that was primarily because of the lack of flow sensitivity. But again, I think from a technical point of view, in retrospect, the flow sensitivity issues are relatively easy to fix, or to improve. I shouldn't call it fix. The must alias analysis is harder, although if you look at what is actually needed in terms of must alias analysis, it appears to be all very local information. Okay, so they're the sound systems, like the type-based systems that are sound. They do their must alias analysis basically by doing name equivalence within a procedure. They track. If you say x equals y, then they know, forward from there that x and y are must aliased until that fact is killed. Okay, and it's only that degree of local reasoning that seems to be needed. All right, so we have not looked at that carefully yet, but I think that even that can be. We can even extend it, to a sound system there and do the needed must alias analysis. All right. For open programs, we do automatic harness generation. Now, our counterexamples, and I mentioned this at the very beginning, it's kind of interesting. So counterexamples are a standard feature of model checking based systems. Ours is not a model checking based system, but we do generate counterexamples in a similar way. But our counterexamples are at the call graph level. Okay, so you don't get a path within a procedure, you get the series, you get the call stack. So here's an example of a race reported in one of our applications. So here's a read, and here's a write, and here's how you get from the harness to, here's the racing series of calls that gets you, that exhibits that. All right, so this is just straight out of the analysis. Here's the pair of, here's the read and write pair, and here's the context, is this call stack. All right.
So if you have k equals 3, how much of the call stack is deeper?
Well, the call stack can be deeper. It's the object sensitivity is k equals 3, but then we can still walk back through the call chain. Separate from the object sensitivity, to figure out who must have called this, who must have called that, and we just do that by looking at the possible parent methods and seeing if they're in a compatible context, and then walking back. Okay. Yeah.
With polymorphic calls, how do you establish context?
Polymorphic calls.
Yeah, if you're talking about libraries.
Yeah, every
simply I can create a class of sound.
Yeah, so I'm not sure if I understand your question, but every method is annotated with a set of contexts that can be called, and those are object sensitive contexts again, and those are the context of the this parameter. so that this parameter can be called,
But you're testing a library. The library
Yes.
may have user-derived classes that you have no control over, and we can't anticipate what they're going to be.
Yes. So I see. How do we deal with the subtyping?
Yeah.
Yeah, we don't. So we don't deal with possible extensions. We analyze the code that's actually there.
Just the code is there.
Yeah, assuming the code there is the code you want, then we can do this analysis. I cannot off the top of my head.
Your harness won't experimentally try to subtype
No.
worst case
No, it will not.
subclasses. No.
It will not. And I'm not even sure how I would approach that. It doesn't mean you can't do it, because I'm very slow thinking on my feet, but I don't see any good way that one could approach that. I mean, the way this would be used would you have some code that that's the code that you're going to run, and then you analyze that code. And if you want to write a new subclass, then you would put it back in for more analysis. Right. Okay, here's some final thoughts. These are just some comments on the approach for those who are interested in program analysis. So this is an example where precise alias analysis is really key, and actually all those phases I used really built on top of the object-sensitive alias analysis. That was the underlying thing that was used in all of the non-trivial phases. Okay, so people have complained for years about lack of good clients for alias analysis. I mean, why does anybody care about alias analysis? Here's one that really stresses the alias analysis and uses it in a non-trivial way. Okay, I mean this really requires a good one. So perhaps it would be useful even for people interested just in alias analysis as a client, as a realistic client. The ordering of the phases is actually important. I didn't mention this, but there was not ad hoc choice of the ordering there. Some of the phases actually depend on each other. I mean, some of them you can't do before others. But the most unusual thing about this, we analyze the locks last. Okay, that's the last thing we do. If you look at most other static analyses for race detection, the first thing you do is compute the set of all locks that are held at every point in the program. That's the first step. Think about a racer. I mean, that's all you do is compute the set of locks that are held. I mean, we don't do that until after we've tried to pare it down through various things like whether it escapes and whether there's aliasing and other things first. Okay, so
It's just a scaling thing, isn't it?
It's a scaling thing, but just a scaling thing. I mean, this is actually, I think, important that we do that last, because we do it on a much smaller set normally than otherwise. Yeah.
Is that a solely performance issue, or is that really a semantic issue?
Well, it's a little bit of a semantic issue, because you have to know that there's at least a shared location before it makes sense to ask whether there's any locks held in common. Right. So you have to do the aliasing piece first.
No.
Right.
If I switch the order,
Yeah.
do I come out with the same set of potential races, and it just takes longer, or do I actually get a different set?
For a suitable redefinition, okay, because some of these analyses, in order to move them earlier, you would have to move them beyond, before things that were needed, and so they would have to, guess non-deterministically or include all possibilities in order to know. You would get exactly the same set. Okay, so it's just a performance issue in that sense, right? Yeah. Okay, and as I've been alluding to all along, I believe it can be made sound. All right, but that's what we're working on now. Okay, and that's the end. So there's a website. You can go there if you're interested. And there's a lot of reports there from developers about the use of the tool. I forgot to mention that a lot of the reports have caused people to overhaul their projects. So several projects have completely redone their synchronization after this. And actually, that's one of the most interesting things, is seeing the response from the developers. And so sometimes, the developers aren't used to getting 50 race reports all at once, and then looking at them and thinking about what to do with that, and having them all be valid races. And so one discussion, I'll mention a couple of discussions that were particularly interesting. One was, geez, these are real races, but if we touch anything, it's going to introduce deadlocks. Okay, we risk introducing deadlocks, and so maybe we shouldn't do anything. Okay, and the variations on that conversation go on for a week, and then finally somebody says, we got to fix these, and so they went and fixed them. Okay. Another one was, another project, perhaps 20 races or so were reported, and it was a mailing list that included developers and users. Okay, and the developer said, oh, geez, these are serious, we will fix them. And the user said, can you fix them now? And the developer said, oh, we got other stuff to do, so I don't know if we can get to them very soon. And then the developers came back and said, okay, here are the patches that fix all these races, please apply them. Okay, so a number of the developers the users went and fixed them themselves because they were relying on it. These were things they were using in companies for mission-critical applications, I assume. And
Have you then done reanalysis to show that they actually fixed it?
in some cases they've asked us to. In other cases where they haven't, we've been spotty about that. We have or we haven't, depending on what they did. Now the one we reported the most, the one with 319, that one they said, oh, it's Christmas. We'll get back to you after the holidays. Okay, and so we're still waiting to hear, about them, what they're going to do. So
what are the issues when you try to apply this to C++?
Good question. So I didn't talk about C or C++ at all. And the reason we didn't do that is because the analysis problem is a lot harder for C and C++. There's no lexically structured synchronization construct. Right? And that encourages people to acquire locks in flow-sensitive and even path-sensitive ways. So path-sensitive just means it depends on some conditional. They'll say if something is true, then acquire the lock, otherwise don't. And if you look in device drivers, for example, especially low-level code, you see a lot of that kind of stuff. Well, I shouldn't say a lot, but you see enough of it that it would cause problems for a tool that wasn't quite a bit more powerful than this one. Right? So we decided to go with Java first just because we thought it would be an easier target for understanding the engineering issues and the algorithmic issues. But I think our experience with fork join synchronization was positive enough that I don't think it's impossible. But I think it's harder than what we've done so far. Yeah.
So how does your work related to your previous work with each-hand on the locking mismatch analysis? The previous each-hand's work.
Each-hands?
Yeah.
You mean Racer X?
No, the lock and lock.
Oh.
You think these?
Yeah. So I know that. That's my previous work too. Yeah, so I know that. So that was more about deadlocks. So that's about avoiding double locking errors, which could cause a deadlock in certain system configurations. So trying to make sure you don't acquire the same thread doesn't acquire the same lock twice in a row. Okay, that's a different problem than race checking. Okay. Yeah.
How many of these could be found using, even much cheaper techniques by, let's say, just something that looks at each class file and looks at which methods are declared to be synchronized. You get any?
Yeah, that's a good question. I don't have a great answer to that. I would take issue a little bit with the question, and not just because I'm a partisan of my own tool, but just my experience with static analysis is that it's not really a question of whether you can do it more cheaply, but whether it's cheap enough. Okay, because once something becomes cheap enough, then once it falls below some threshold of cost, people don't really care how much effort you're spending, whether it's an extremely fancy algorithm or an extremely cheap one. So I think this is almost cheap enough. Except for this last one where it's something you probably you might. Huh?
Make it part of your nightly build. It's in the noise.
Yeah, these are build level. These are things you could run in the nightly build.
It's cheap 26 minutes. That's dirt cheap. It was more of a question of.
Right. Would you want to be cheaper? You need cheaper than dirt.
Well, I'd like to. It was just for you to characterize what kind of flags there are. Are there?
Well, they're highly context sensitive. That is one thing. It happens in certain contexts. Sometimes people will be putting in a lock here and a lock there. It's only by calling these things, and kind of skirting around the locks that you get the race. There's a lot of bozo races, though, too, where, in the classic one in Java is, they put, this kind of like the example I gave. They put a lock on the right, and they don't put a lock on the read, thinking that somehow, they forget that it's a pair of things that interact, and both of them have to hold the lock. Okay. So now in terms of fractions, I can't give that to you. There's certainly a big chunk like that, and there's a big chunk that are subtler, that are hard to see. I would say the ones that are hard to see are more hard to see just because the code is spread out. Typical with these kinds of bugs in big systems, it's just because the information is not localized in one procedure. It's this procedure calls that guy, which calls this guy, and they're textually far apart, and that makes it hard for humans to spot. Yeah.
So did you try to experiment with k equals 1, 2, 3, and maybe a 4?
Oh yeah, we did. That's how we got k equals 3. Yeah, you just think it back and forth. And okay, that's the best one.
So why is the best?
Well, because presumably, the intuition I gave with the hash table I think is most useful. It allows you to distinguish the depth of it gives you context sensitivity to some depth in your data structure. And people don't build many structures of depth deeper than 3. Where you have, 3 major types of objects pointing to each other. So, I mean, this is different than saying, so I want to be clear about this. I mean, if you have a linked list of arbitrary length, that doesn't count. That's all at one level from this point of view. Okay? The point is, when do you call a constructor that calls another constructor that calls another constructor? I mean, it's that chain. How many nested chains of constructor calls do you have? And depth 3 seems to be pretty good. Okay? Sure, you can construct things with depth 4. In our experiments, it didn't make any difference. We crank it up to depth 4, we don't see any improvement in the...
So worst case, increasing K could be very expensive. What do you find it is practical?
Well,
in terms of runtime cost?
Well, these numbers are here for K equals 3.
Yeah.
And, I don't know the answer, actually, for how many of these terminate with K equals 4. Okay? I can say pretty confidently that they all terminate except Derby. And I just don't know the answer for Derby. I've forgotten right now whether certainly for the ones that we could run with K equals 4, it made no difference. Okay, I know that for sure. And I just don't remember. I'm sorry, I just forgotten whether we ever tried Derby with K equals 4. But it is...
Terminate, it's just whether you have enough patience is very question, right?
Well, terminate in the, when I say terminate, I mean in the practical sense.
Okay.
I mean whether you can stand to wait, whether the paper deadline comes before it finishes. I mean, that's kind of the notion of termination that I use.
Have you thought about using annotations to help some of your cases? In particular, like escape analysis that could benefit a lot from annotations.
Well, it doesn't seem to be a problem right now. I mean, we haven't considered annotations for anything except other synchronization patterns that aren't naturally captured by the kind of flow insensitive base that we have at the moment. Okay, that's the only thing where we've considered annotations. I'm actually in favor of annotations. I don't mind annotations at all, but I also recognize that you want to be very parsimonious, and you don't want to inflict them unnecessarily on people. So we try to add only those annotations that we think are really necessary.
When coming up with your set of unlocked heads, did you find there was a statistically higher number of read writes versus write writes?
I don't know. That's a good question.
You want the breakdown?
That's a good question. I could find that out for you. We didn't check that. We didn't compute that. That would be interesting to know too.
There's something very interesting that I find overall in this technique as opposed to, say, using any static analysis. So if you run any static analysis and data flow analysis or model checker, then typically with respect to time, it's going to find more and more bugs.
Sorry, with respect to what?
So if you run, say, any data flow analysis across a loop, or say you run model checker, then with respect to time, as time proceeds, then it keeps finding more and more bugs. Mm-hmm. But here you're assuming like everything, you're assuming that everything is possibly is a bug, and then with respect to time, you're kind of filtering things out.
Yes. Yeah. So instead of, we're sort of taking a kind of a greatest fixed point approach instead of a least fixed point approach. And this is more of a type theoretic view of the world. I mean, typically in a type-based world, you start out with these type variables that could stand for anything, and then you start unifying and restricting the set of things they could be. Okay? And it also goes very much with a more compositional view of analyzing open programs. Like I analyze this piece, okay, and that's going to give me a set of possible worlds, which when I add another piece is going to suddenly get smaller as I constrain it. Okay, now we're not really doing it compositionally. These are all implemented as whole program analyses. But you're right, there aren't a lot of other examples, at least to my knowledge, that take this view of first enumerate everything bad that could happen and over approximate and then remove things. Yeah.
So do you have an assessment of how important it is to use the BDD representation?
I don't think that that's crucial. I think the BDD, these are all implemented as data log rules. The relations underneath could be solved in other ways. There's no doubt about that. In fact, some of our engineering problems have been with BDD. So one thing that happens with some bigger programs, I mentioned this to Manuel at lunch, so BDD uses 32 bits to represent the set of contexts, so you can only have 2 to the 32 contexts. And actually some big programs, there's more than 2 to the 32 paths to reach a particular point buried deep in the program. And so it overflows the number of bits that are available to represent a set of contexts. You have to either move to a 64-bit machine or something. And so we've had some problems like that. there's no question that this approach, this context-sensitive analysis and things like, the things that can deal with it, like BDD, BDB, whatever it is, that this is very useful. I mean, so maybe it's not the best, ultimately, maybe it's not the ultimate way to implement these things, but it's extremely useful for these kinds of analyses. And this context-sensitive information is really important for these bug finding tools. I mean, it's not so important, I think, for optimization, but for bug finding, you really need it.
And for that purpose, I'm thinking if you're just based on a single type-based heuristic, say if you go up 3 level and just look up the type, how effective would that be?
3 levels where?
3 levels going up the call chain and look at the type where that object is constructed, compare the type.
Yeah, well, that sounds like control flow analysis to me. I mean, sort of standard ML-style polymorphism. And we tried that, and we couldn't find a K. I mean, so one thing about the BDD approach is that it does require you to pick a K. Right? I mean, you really need to, you have to bound it in some way. Okay? And there was no good K. I mean, that's why object sensitivity just turns out, for object-oriented programs, I think object sensitivity is just a much better notion of context sensitivity. For a smaller cost, it gives you a more precise answer. There's no reason you couldn't combine that with other notions of context sensitivity. So yeah, you could have control flow analysis and object sensitivity, but we didn't find that necessary. Okay. That doesn't mean it's not a good idea, but we didn't run into that. Any other questions? Well, you've been a great audience. I thank you for listening to my talk, the first time I've ever given it. So I'm sorry I was a little bit rough around the edges, but I appreciate your attention. Thank you.